this computer. Okay, so here we go, 11.1. Functions of several variables. So imagine, if you will, our z component is a function of x and y. So we say z is a function where we can input two scalars into. We can input x and we can input y. And our output is another scalar, right? In this case, we can think of it maybe as our z component in R3. The variables x and y are independent variables. And z, in this case, is the dependent variable. Right? So z necessarily depends on the values of x and y. So let's talk about domain and range. This is a concept that we've talked about in Calc 1, but let's kind of bring it up to speed and what domain and range kind of change in higher dimensions. So now the domain is defined as all points of x and y that our function f of xy is defined for. The range is all z equal to our function f of xy values that our domain allows for. Okay, so we have a question about the quiz that would be on tomorrow. Because we're just taking an exam, I'm just going to say that there's no quiz. Yeah, our next quiz will be next Tuesday. Okay, so let's look at some examples. So we'll have a function column, a domain, and a range. So our first function is z is equal to the square root of y minus x squared. Our second function will be z is equal to 1 over x times y. And we'll have one last function where z is equal to sine of x times y. So remember, the domain is what things I can put into my function, what's allowed. So I look at this first function, the square root of y minus x squared, right? And I want to figure out what can I put into here? Well, we're looking at this radical, and we should realize that we can't really have a negative inside this radical if we're going to restrict ourselves to the real numbers. So I need y to be greater than or equal to x squared. So this gives us our definition for the domain. It's all x and y values such that this is satisfied. For the range, it's all possible values where if inside my domain, I can get out of my function, right? So what z values can I possibly get given that this is my domain? Well, if y is equal to x squared, this is certainly 0, right? I shouldn't be able to get any negative numbers out of this, right? There's no values inside this radical that will give me a negative or purely real negative number. So we know that we should include 0. That's the smallest thing that we can get out of this. What's the largest thing, however? Well, I could set x equal to 0, and I can let y scale up as large as I want, right? Making z as large as I want. So it looks like I should go from inclusive 0 to exclusive infinity. So technically, you can set the function equal to 0 and solve. If you're talking about solving for the domain, in this case, sure, but we have to be a little bit more conscious than that. See, this next function is kind of an example, right? I don't want to set this really equal to 0 and solve for what x and y can be, because the prohibitive part of 1 over xy is when the denominator is 0, right? I can't have that x times y, this product, equal to 0, or I have 1 over 0, right? So the restriction here is that this product cannot be 0. And there's other ways for us to write that. Because x and y exists in R2, we could say, R2 minus when x or y is equal to 0. So now for the range again is the values of z that are allowed given our domain. Well, imagine that y is some constant value that's not 0, right? Maybe it's 1. I can let x be as large or as small a negative number, right? So I can certainly get a negative number for z, right? So maybe I let y be 1, but I let x be 1 over, or negative 1 over a billion, right? And I make that increasingly more and more small. So I can definitely approach negative infinity. But is there any value that I can pick for x and y to get z is equal to 0? I can't. I can't pick any x and y that lets z be 0. So I have negative infinity, x or exclusive of 0, but I also can do the exact opposite. I can go from 0 to positive infinity by that same argument, right? So I can do the union, that's what this u means, of 0 to infinity. Right, so it looks like I can do almost any real number except for 0, which is another way that we could express this. So now looking at our third function here, I have sine of x times y, right? So I'm looking at this and I think about what kind of values are prohibited in the sine function. None that I can think of for real values. So now I'm thinking, okay, so there's no restrictions on the x and y product, but there doesn't seem to be any kind of restrictions on the inside as well. So that means that all x and y values should be allowed here, and one way to write that is just writing R2. So all possible real numbers in the x, y plane are allowed for this. Now for the range, no matter what x and y are, they're still inside this sine function, right? And we know the range for sine functions of one variable, right? So it shouldn't be any different here because this x times y is still some scalar value that it's inputting into sine. So the range here is -1 to 1, inclusive of these endpoints. So we can also extend this idea to higher dimensions as well. We could extend this idea to higher dimensions. So let's look at another set of functions. This time we'll be in R4. So these will be functions of 3 variables. So maybe we say that W is equal to the square root of x squared plus y squared plus z squared. So our function here is x squared plus y squared plus z squared under this radical. Maybe our next function is 1 over x squared plus y squared plus z squared. And then lastly, maybe we have w is equal to x times y times the natural log of z. All right, so looking at our first function, what's allowed? What x, y, and z can I input into this function? Well, I got to make sure that what's inside the radical is going to be a non-negative scalar. But I look at x squared, and I look at y squared, and I look at z squared, and because they're squared, any real number that I input into those is always going to be positive, right? So in fact, their sum doesn't really change any of that, right? We're always going to get a non-negative number in there if I put a non-negative number in there, or sorry, any number. So it looks like the domain here is R3. All values of x, y, and z are allowed. And that makes sense because this is very reminiscent of our distance formula. All right, so for the range, if I'm always getting a non-negative number outputted from x squared plus y squared plus z squared, the square root isn't going to change that. So I can certainly get 0, and I can certainly make x, y, and z large enough or that I'm approaching infinity, right? So I can make x, y, and z increasingly large. So notice here that our domain was always the dimensionality of our function, right? So if I input 2 variables, we'll kind of scroll up here for a second. If I was inputting 2 variables, I existed in R2. Here I'm inputting 3 variables, so my inputs exist in R3. But in this other column, my range always looks like it exists in just R, right? And it's the same here, right? Because we're outputting a simple scalar, right? W will always be a scalar value once we input x, y, and z. Okay, so now for our second function, we have 1 over x squared plus y squared plus z squared. I can't have the denominator be 0, right? So it looks like if I have that x squared plus y squared plus z squared is 0, then I would need all 3 of those coordinates to be 0. So what I can say is the point x, y, z does not equal the origin, 0, 0, 0. So the domain for this is essentially R3 minus the origin, right? That's the only time that I get 0 for the denominator, right? I can't have x, y, and z all be 0. For my range, well, just kind of similar to the example we had above, there's no combination that we can choose of x, y, and z to get 0. We can't manage it. So we know that 0 is not in the range. There's also no x, y, and z that I can choose to make this a negative output because they're all squared, right? No matter what, my denominator is always going to be a positive amount. So it looks like we don't have any negative numbers and we can't get 0, but we can make this increasingly large. So it looks like we can go up to infinity by choice of our x, y, and z. All right, so now for our final function, we have x times y times the natural log of z. So my eye is kind of drawn to this natural log. I don't see any problem with x times y for my domain, but I look at this natural log, and for the real numbers, I know that I can't really deal with these negative quantities, right? So I certainly can have z restricted. So z equals 0, so we can do here as well. So we can do negative infinity. Oh, in fact, wait. Shouldn't have that little tick. Okay, so we have their outputs being negative infinity times infinity, because I can choose any x times y, right? So I can have x be increasingly large in a negative number to get me some negative infinity, and vice versa with y. I could also just do a positive amount of these x times y's, and I can have that I get increasingly large here. Okay, so let's talk about graphs. Because when we had functions of one variable, we kind of thought about what that y equals f of x looks like. So if f of x and y is a function with domain D, then the graph is a surface generated by the collection of points x, y, and f of x and y. Right, because we're setting the z coordinate equal to this function here. In R3. So anytime I put in an x and a y coordinate, I get this z component here. Right? And the collection of all of these x's and y's will generate this surface. So an example would be to graph the function of x and y, which is equal to 100 minus x squared minus y squared. Another question to ask ourselves is, what kind of surface is this? But let's wait. Let's get a feel for what this thing looks like. So if I have 100 minus x squared minus y squared, one way to kind of think about this is, remember, we're setting z equal to f of x and y, which in this case is 100 minus x squared minus y squared. Well, I can rewrite this as negative z is equal to x squared plus y squared minus 100. If we look back to some of our categorizations from chapter 10 of these kinds of surfaces, this was an elliptic paraboloid. Okay, so that kind of gives me an idea of what this looks like, but let's be more exact with this. Let's look at this function in detail. So we have our x, y, and z axes here. So I can write all the way down here. Okay, x, y, and z. So if I look back at my definition of z equals 100 minus x squared minus y squared, so I can kind of think about the domain and range of this function. Well, I don't see any problem with inputs from x and y, right? So it looks like I should be able to input any x and y into this. So the domain should be R2. Now the range, however, I should be a little bit cautious because I have 100 minus, and I can write that as 100 minus the quantity x squared plus y squared, like that. This thing is always going to be positive, right? So that means that the largest value that I should possibly be able to attain is 100, because I'm always going to be subtracting a non-negative number from it, right? This can be 0, or it could be larger than 0. So the maximum I should be able to obtain is at 100. And that should happen at 0, right? When x and y are both 0, I should get this 100 point. And what happens when, say, x is equal to 0 and y is equal to 10? That would give me 0. So if I'm at y equals 10, I don't have any z value left. Vice versa, if I have that, y is equal to 0 and I have x is equal to 10, I also hit z equals 0. In fact, you can kind of think of this x squared plus y squared as like an r squared. The radius from x and y is equal to 0 out. So in fact, that's kind of makes this circle here. Actually, let's draw it like this. And then we'll do some dotted lines behind it. So this is where z is equal to 0 along this line on the xy plane. Right? And this actually, because we know this is an elliptic paraboloid, kind of takes a that's kind of messy, but it's a kind of like this parabolic shape here. And this kind of extends past as well, right? So it keeps getting larger and larger as we kind of go down. Now, of course, I can't draw, obviously, that well. If you also can't draw very well, you could use, there's a lot of different types of programs that can help you plot these functions in R3. Mathematica is one. It's a very powerful tool. We used to kind of require students to kind of get familiar with Mathematica for Calc 3. We're not going to do that for this semester, although you can ask me questions about Mathematica if you want. It's a very powerful tool. You have free access. You're a student. Might as well get it. Okay. Oh, in fact, the next thing I do is computer plots. Oh, no. We're going to do that next. We're going to do level curves, and then we're going to look at some computer plots, just because my drawings are horrible. So some level curves. So imagine oh, thank you for the encouragement. This is a pretty easy function. I don't think I could be able to draw the other ones. We're going to look at some computer drawn surfaces in a second. Plus, you'll get to see kind of maybe how you'd want to do that on Mathematica. So imagine we have a surface generated by z is equal to some function of two variables, this x and y. The level curves are all curves where f of x, y is equal to some constant. Well, we'll call this constant k, although it doesn't quite matter. So what this kind of means is, imagine you're setting z equal to some constant, right? So at our above plot here, if I said that our constant k was equal to 0, and I want that level curve, right? I want that level curve when f of xy is equal to 0. That would give me this circle down here that we've kind of sketched out, because that's every single spot where the surface has a z component of 0. Maybe I wanted the level curve 100. The level curve for 100 would be all of the collection of points where z is equal to 100, which is just the single point at the top of our surface here. Right? And you can imagine maybe you set it equal to somewhere in between 0 and 100, and you'd get another little circle from in here or below it. So basically, it's kind of like this trace where you cut at that very specific z equals k level, right? And then you see the curve generated from x and y that generate that specific constant value for z. So now, if we plot multiple level curves onto the x and y plane, this becomes a contour plot. That's not how you spell contour. There we go, contour plot. Much like elevation maps. Right, so if you've got this elevation map, maybe you're hiking, you're looking at it, it's on a sheet of paper, right? You can only limit yourself to R2. And it tells you an X and a Y coordinate, and then it tells you certain instances where you have these level curves, where the elevation is all constant, and you can kind of follow it, and you're like, oh, around these X and Y coordinates is where the elevation is a constant. And then you can kind of read out the shape almost of the surface that you're looking at. It's kind of like if you're looking down at the surface from above. Okay, let me pull up Mathematica, and we'll generate some curves here. Just give me one moment. Double check. This is a good domain and range to use. Okay, let me pull over. Oop. Keep messing up my window. Here we go. And then change our share. New share. Let's do Mathematica. So these are some of our old ones that we did the other day. But here is our first function that we're going to take a look at. So you can do contour plot. There's also plot 3D. That's also pretty nice for Mathematica. Contour plot's pretty nice because you can actually see these contours if you wanted to look at it from above. So here we're looking at e to the negative x squared minus y squared. And you can kind of imagine that you look at it from the side. This looks like a lot like just e to the negative x squared, or e to the negative y squared, depending on if you do it from whatever angle. That is actually called a Gaussian. Fun fact. It shows up a lot in math and physics and other math-based sciences. And we can kind of look at it from above, and we can see these contours now. We can kind of think of this x squared and y squared again as this like radius-like entity. And they'll increase at the same kind of rate here, right? So that's why we see these circles. Okay, so let's look at another function. This time we'll do z is equal to cosine of x plus sine of y. Ooh, and let's do -6 times pi, gotta be capital, 6 times pi, and we'll just repeat that for over here, just so we can get the whole kind of image that's going on. Oh my goodness. Maybe it was too big. Anyway, look how crazy that is. You can kind of look at it from above. Maybe let's reduce that. Let's reduce that just a little bit. Let's just do 2 pi. Too many spikes. So this is kind of what's happening here. Right, and you can kind of think about where this function is equal to 0, and you can kind of see it on the z-axis as I'm kind of rotating it there. It's wherever cosine of x is equal to negative sine of y. Right, so you can actually think of, actually you can see it on the contour here. This is one instance right here, this where this crosses is where it's equal to 0, and you can follow those contours. They actually end up being straight lines, which is really cool. Right, so if you look at it from above, you can kind of see this pattern, and anywhere you see those straight lines, that's actually where the function is equal to 0. Otherwise, you see these general, like, not quite circles, and because they start to get deformed as they move away from their peaks. But pretty interesting, right? You have this so it's not cosine of x times sine of y. It's this addition of the two. So you'll see that the magnitudes of these guys are -2, and let's scroll up just a little bit, to +2. Pretty cool. Okay, so let's look at another one. That will be our last one for now. We're going to do sine of x over x. Oh, and I do this multiplied. So times sine of y divided by y. Oh, and I got rid of my bounds. Oops. Let's put those back in. That one should be x. Oh, shoot. What have I done? Okay, so this is what our function looks like. This sine of x over x times sine of y over y. And these vertical strips that you see here are when x and y are equal to 0. Right? So notice here on this axis we have 0, and over here we've got 0. This is just Mathematica trying to figure out what the heck is going on there. The functions are undefined along those lines. We can't have x or y be equal to 0. Right? So basically those two lines that make this cross. Otherwise, as we move away from the origin, we get smaller and smaller. So you kind of see this decay outward. Let's do a little bit larger. See if we can see. Yeah, okay, there it is. So it's having a tough time kind of visualizing what's going on here. But we still see these straight lines. We can't have y or z be equal to 0. But notice that we also have these kind of oscillations that are being caused, right, along those lines. That's because of the sine of x and sine of y. So along each one of here, these are being multiplied together. So anytime we have sine of x or sine of y being 0, we get 0. But they're also slowly oscillating even though they start to decay as x and y become larger. Okay, with that, why don't we take our 5-minute break, and then we're going to come back, and then we're going to do some matching. So I'm going to give you guys a little bit of time. We're going to do some matching of some kind of diagrams that we're going to pull up, and then we'll move on to and start section 11.2. All right, so go get a drink of water, go use the restroom, and we'll be back in a little bit. Okay, so there's a few questions. Will there be any new material on this exam? No, it's still going to be chapter 10. Yeah, the only new material is just what we've been talking about today, and that's just going to be grouped in with the second midterm. Would you consider releasing the solutions to the test for a study guide? Unfortunately, I can't put them out right now, but I could release them once a few events have unfolded. Okay, so on further thought, the matching, I think I'm going to give to the TAs, because I think that's a really good group activity to do, where I'll give you some contours and some surfaces, and you kind of try to match them with the functions that are represented by them. Okay, so with that, we're going to stop 11.1. So the first section of every chapter is just so nice, so simple. So now we're going to talk about limits and continuity. So let's do a new page here. (11.2). Limits and continuity. If a function now has two or more variables, we denote the limit to the point oh wait, we denote, oh sorry, skipped a word there. We denote the limit by the approach to the point. So rather than you have some limit, say, in when you have functions of one variable, you're letting x go to, say, a, you might now have what we'll kind of write as the limit as the point of x and y goes to some other point that we'll call x naught and y naught of our function. And maybe we'll say that this is equal to L if the limit exists. Right, but this is how we denote some limit. And this is actually a lot harder than the limit for a function of one variable. Because for a function of one variable, if we had some curve, right, and we wanted to know the limit, we would come from this side and we would come from this side. And then we could be able to figure out what the limit is here. Now imagine that I'm looking down on some function here. So you can't see the elevation here, but this is kind of maybe our domain around the point. And I want to know what the function is doing in the limit at this point here, right? We don't no longer have kind of this duality. We don't have from the left or from the right. We've got from the bottom, we've got from over here, we've got from over here, or over here, or over here, or maybe it does something like this and it loops around and then it finally comes this way. There's an infinite number of paths now to take. So how do we kind of deal with that? Well, let's do the strict kind of mathematical way of kind of defining this, and then we'll kind of figure out what that means for us. So we can say that the limit as x goes, or xy goes to the point x naught, y naught of some function of x and y exists and is equal to some value L if for every, and this is an epsilon, for every positive epsilon there exists a corresponding number that we'll call delta that's also positive, such that for all points x and y in the domain of our function f, we have that the square root of x minus the limit point x naught squared plus y minus the limit point y naught squared So notice this is kind of representing the distance we have, and it's bounded between 0 and our delta. Implies that the magnitude of f of x and y minus L is bounded by epsilon. Okay, so this is kind of the math way of defining that, right? And if you haven't seen this epsilon and delta notation before, this might be confusing. So let's talk about kind of what this means. What's the layman's terms for this? This means if we pick an epsilon, we can find a circle around our limit point x naught and y naught, where all of the values generated by x and y inputted into our function are less than an epsilon difference between L. So let's kind of draw our box again here. So we're kind of just looking down. So we don't actually know the elevation of the function that we're looking down on here. But again, imagine we're trying to find the limit as we approach some point here, maybe close to the center. The idea is if I have circles, right? So maybe this is some circle that's presented by delta, right? Everything in this circle means that there is the difference between the limit point and the function of all these points in here, right? The range of this is less than epsilon, right? So if I want, say, maybe a really, really small epsilon, I should be able to make this circle smaller, right? And then maybe I make that epsilon even smaller, which means I should be able to write a circle that's even smaller, right? So as the circle gets smaller, I'm getting closer and closer to my limit point, which is exactly how we kind of define limits in the real math way for functions of one variable. But it's easier to think of I'm coming from the left, I'm coming from the right, rather than a circle of some radius in that like R2 way, right? But now we're kind of looking down above it and we've got these circles. And we can use this same definition for functions of more than one variable, in fact, where we'll have spheres and hyperspheres, what have you. But we're trying to make this circle smaller and smaller as we let epsilon gets closer and closer to 0, meaning the difference between the limit point and all possible values in that circle are getting smaller and smaller. So I'm approaching the limit point as my circle gets smaller. Okay. So some more talk. So notice the path we take to get to the point x naught y naught does not matter if the limit exists. So regardless, if this limit does exist, regardless of my path to this point, I should still get the same thing, right? So no matter which, if I go in a straight line towards it, or maybe I come like a parabola into it, or maybe I just do a bunch of squiggles and I finally get there. Regardless of the path I take, I should get the same value as I travel along that path. So that brings us to another little statement. So if f of x, y goes to, represented by these arrows, L as x and y goes to x naught, y naught by path C1 and f goes to, oh, we should put an L1 here. If f goes to L2 as xy goes to the point x naught, y naught by path C2, the limit of our function does not exist when L1 does not equal L2. So if I can travel along a different path and get that the function approaches a different value, that means that the limit does not exist, right? I can't take two different paths and get two different limits if the limit exists. Okay, so let's look at some examples. Let's look at the limit as x and y go to the point 3, -4 of the function x squared plus y squared. So in this case, we know that there aren't really any kind of restrictions on the domain for x squared plus y squared. So it looks like 3 and -4 should be fine. In fact, we'll talk about continuity in a little bit, but we can kind of generalize for now the idea of how continuity works for these things, right? The square root acts on a scalar value, right? And if I even just plugged in 3 and -4, I know that x squared is a continuous function, so I should be able to plug in 3. I know that y squared is a continuous function, so I should be able to plug in -4. And as long as I don't have negative numbers in the square root, it's also a continuous function. So if I just plugged in those values, I would get the square root of 25 or just 5? Now that's the easiest case, right? It really worked out. We just plugged in those things and we got this limit point. Okay, so now let's look at another example. For this time, we're going to have the limit as x and y go to 0, 0. In this case, my function is going to be x squared minus x times y over the square root of x minus the square root of y. Okay, so now I look at this. My first thought, can I plug this in? Ooh, okay. So that denominator there, that square root of x minus the square root of y, that's going to cause some issues if I plug in 0, 0. Okay, so it looks like my domain does not include 0, 0. So we have to be a little bit trickier here. What is my function approaching as it goes to 0, 0? So there's a few ways we can try to do this. And to follow the kind of logic from Calc 1 when we dealt with these kinds of limits is, can we remove that singularity? Can we get rid of that problem with the denominator? So we just can't plug in 0, 0. But what we can do is we'll look at our function. And we have the square root of x minus the square root of y on the denominator. What I'm going to do is I'm going to multiply by a special looking one. I'm going to have the square root of x plus the square root of y in the numerator. And then to make it 1, I need the same thing in the denominator. So this is just 1. I'm just multiplying by 1. But here on the top, I get a x squared square root of x. Well, I'm actually going to, Actually, I'm going to factor an x out of here. So we get x times x minus y. So that's just rewriting the numerator as is. And then I multiply by the square root of x plus the square root of y. And then in this denominator here, there's a reason we did the alternate sign, right? So I had the square root of x minus the square root of y. Well, when we FOIL this out, those cross terms cancel. So the thing that I'm left with is just x minus y. But then look at what happens with this numerator here. I have this x minus y, and I have this x minus y here down in the denominator. So I can cancel those, and I can say that this is equal to x times the quantity square root of x plus the square root of y. So this, however, does not have a problem with me plugging in 0 and 0. So we plug in the point 0, 0 into here. We get 0 times the square root of 0 plus the square root of 0 is 0. So this means even though our function doesn't include the origin 0, 0, the limit as the point xy goes to 0, 0 of x squared minus x times y over the square root of x minus the square root of y is equal to 0. This is how the function approaches. And a cool thing about this is it approaches 0 from any path that you can take towards 0, 0, the limit along that path will be 0. That's pretty cool. Okay. And let's list some properties. What are some of the properties of this limit? So if the limit as x and y goes to x naught, y naught of the function is equal to L, meaning that it exists, and the limit of x and y going to the same spot x naught and y naught, but of a separate function we'll call g of x and y is equal to, say, m. So this also means that it exists. Then we've got some properties. And I'm gonna leave out the whole business underneath the limit just to save a little bit of space and time. So we have here that the limit of f of x and y plus g of x and y is equal to L plus m. So the limit will distribute to these as long as they exist. And then this is L here. And then this is m here. So we just have L plus m. So as long as the limit exists, we can kind of not multiply out, but apply the limit to each of these individual sums. So another property is if I have the limit of f of x and y, and it's multiplied by g of x times y, so long as the limit of both of these exist, which was our kind of precursor here, then this is the limit as the limit gives us that L times m. So as long as both of these have limits that exist, then we can write it as their product. Another is if I have the limit of f of x and y, and I divide this by the function g of x and y, again, so long as f and g have their own limits, then I can write this as L over m, so long as m does not equal 0. And finally, if I have the limit of f of x and y, and it's raised to some power m over n, this is equal to L of m over n, so long as m and n are integers. And L is a real number. So these are a lot of the same properties as limits of one variable, but now we kind of get this idea of, yeah, they still kind of work in the framework of multivariables. Okay, so let's do another example here. This time, we're going to show the limit as x and y going to the origin of the function 2x squared times y all over x to the fourth plus y squared does not exist. Okay, so this is a little bit different than the other examples we were talking about. Now we're trying to show that the limit of this thing doesn't exist. So going back to what we said earlier, remember the limit doesn't exist if we can take two different paths and we get two different values, right? So I'm looking at this and maybe I can kind of find two paths that have different limits along them. So how do we even kind of formulate that? So what we'll do is we're going to say we're going to approach zero, zero along the curve y is equal to some constant k times x squared, so long as that constant doesn't equal 0. Right? This includes the point 0, 0. Right? And k just kind of scales the slope of that parabola, right, in this xy plane. So I'm going to travel along this curve and see what my limit is. So how do I do that? Well, first, I note that my function evaluated when y is equal to k times x squared. So I have 2x squared times y all over x to the fourth plus y squared. And then I'm evaluating at y is equal to k times x squared. So I just, wherever I see a y, I just plug in this k x squared. So the numerator, I get 2x squared times k times x squared. The denominator, I get x to the fourth plus k squared x to the fourth. So maybe you can kind of see why I picked this y is equal to at least this x squared here. This simplifies, and I get 2k and 1 plus k squared in the denominator. Okay, so that's my function evaluated along this line. Cool thing about it is that it's a constant. It's a constant with respect to k, right? So no matter what x and y I pick along this path, I'll always get this value. But k, so wait, let me back up. We have to make the limit case now, because we're saying now the limit of x and y going to the origin, and we'll put down here along y is equal to k x squared of f of x and y is, well, I can definitely plug in x and y into this. It's just 2k 1 plus k squared. But k can be any real number. right? Maybe I chose the path where k is equal to 1, right? I went along y is equal to x squared. And then I get 2 times 1 plus 1 plus 1. So I would just get that the limit in that case would be 1. But if I slightly increment k, maybe I say it's even 2. Y is equal to 2x squared. I get this 4/3 as my limit. Right? So this changes the path. I still get to 0, 0, but I change the path and I get a different limit. So we get different values of the limit along different paths. So that means that this limit can't exist. I get different values for different paths. In this case, I just chose a pretty nice general path, right? Where I can just change k a little bit and get a brand new path, right? How did you know that y was equal to x, or sorry, k x squared? It's not a it's not that I knew that y was equal to x k squared. I just came up with a path in the xy plane. So you could do, say, y is equal to x and then y is equal to 2x, something like that. And you just prove that any two different paths get you different limits. In this case, I put in this parameter k, so I could just change my path however I see fit, right? I can change the path by just putting in a different k value. So this is actually an infinite number of paths to 0, 0 that I could possibly take. But you could choose different types of paths. As long as you can prove that two paths give you different limits, you can show that the overall limit does not exist. The reason I chose x squared is just this problem was like a little bit contrived, right? If you plug in y is equal to kx squared, you get this really nice thing here. But maybe I plugged in x, and then maybe I plugged in sine of x or something like that. And I take the limit, and I get two different values. Okay, so that also kind of brings up this idea of when to use this type of logic, right? Here, I'm trying to prove that the limit does not exist. In order to do that, all I need to show is that the limit along two different paths give us a different limit. If I had chosen two paths and I got the same limit, that does not mean that the limit exists, nor does it mean that I'm done. Right? If I chose two different paths and I got the same thing, that doesn't mean the infinite number of paths available provide the same limit. You might have just accidentally picked two paths that got you the same limit. So it's really hard to prove that a limit exists using this type of behavior or kind of methodology here, right? I can't just pick arbitrary paths and then say, oh, the limit is definitely this along this path. No, this is how we can disprove that the limit exists or prove that it doesn't exist, right? All I need to do is show that two paths give me different limits. Okay, so now that we've talked about these limits, let's define continuity. And then after that, I think we'll kind of call it for today. So for continuity, we have that a function that we'll call f of two variables is continuous at the point x naught and y naught if the limit as x and y goes to x naught, y naught of our function x, f of x and y is equal to the function at that point. And that's how we've defined continuity for functions of one variable, right? If you just plugged in those limit points into the function, you should get the limit, right? And that means we are continuous at that point. We say that f is continuous on some domain D if f is continuous at every point x naught, y naught in D. So same type of definition that we use for functions of one functions of one variable, and we're just generalizing it to functions of more than one variable. So note that polynomials which we did kind of define as some sum of polynomial-like terms of x and y are continuous. On R2. While rational functions which are defined by some polynomial in the numerator and then maybe some polynomial in the denominator, are continuous everywhere probably not the best that I use B twice there. Just call that D. That's just some coefficient out in front. So more or less, this says if you have a polynomial on the top and you have a polynomial in the denominator, it's continuous everywhere where this condition is met, where the denominator is not equal to 0. And we kind of already knew that, but it's nice to say that it's continuous everywhere except where the denominator is equal to 0, right? So we're going to use that type of logic moving forward because we'll know that it's continuous everywhere except maybe some given paths. Okay, so then with that, we're going to conclude today's lecture.